We're starting Chapter 5, Section 1, Integrals and Antiderivatives. So what is an antiderivative? We see the definition here. So you need to kind of process this and think about it. F is an antiderivative of little f if the derivative of big F is little f. Now, make sure that starts to sink in. So what you have to think of, antiderivatives are like backwards derivative. So if this statement here is true, what does it mean? It means that f of x is the derivative of a function. So you're told you have f of x, that is the derivative. So the question would be, well, if that's the derivative, what did it come from? What was the original function? The original function would have been capital F of x. How do you know? Because when you take the derivative of f of x, big F, it equals f of x. That's how you know you did it correctly. So you know you got the correct antiderivative if you take the derivative of the antiderivative and you get your function. So we're just doing a backwards derivative, and the notation, f is the backwards derivative. How do we know? You take the derivative of f and it comes out with what you have. So here's an example. We have a function and someone says, hey, this is the derivative of a function. What was the original function? So you're going to have some rules to help you out here, but right now you have to think backwards. Well, where would that come from? I know when I take the derivative, I decrease that by 1. So where it came from must have been a 3. So it must have been a cubed. And so if I take the derivative of this, the 3 comes in front, and the power decreases by 1, and that matches that. So I have found that one. But then the question, what did this come from? And we know when we take the derivative, the power here is decreased by 1. So what we had originally had to have a second power. And so we say, okay, maybe it was x squared, and to double check that, we take the 2, move it in front, decrease that by 1, and we do get that. And then we ask ourselves, the derivative of what ends up being 1, and it's x, because the derivative of x is 1. So this would be an antiderivative. And how do we double check? Again, you take the derivative of this, and you better get that. So in other words, the derivative of f prime, which is this, better equal our original f. So kind of get your head wrapped around that. It's kind of weird the way they state it, that the derivative of big F is little f, but it should make sense once you kind of process through that. Now, here's the part that you have to think about. What if someone says, hey, that's your f of x, or excuse me, yeah, that's your f of x. My brain, sorry. This is your f of x right there. My f of x is this. Who would be right? And if you take the derivative of this, what do you get? That's 3x squared, bingo. That's 2x, bingo. That's 1, bingo. And the derivative of 20 is 0, so they're both right. This is an antiderivative, and that's an antiderivative. But someone else says, hey, this is my antiderivative. Well, let's check. The derivative of that is 3x squared. Bam. The derivative of x squared is 2x. The derivative of x is 1, and the derivative of 10 is 0, so that works. So what you should see here is there's an infinite number of antiderivatives. Multiple, because you can have all kinds of constants, because when you take the derivative of a constant, it comes out 0, and it's not there in the derivative. So you could have had any constant to start with, and when you take the derivative, you end up with the same function. So antiderivatives aren't unique. There are multiple, an infinite number. It's called the family of antiderivatives. So let f be an antiderivative, big F be antiderivative of little f. Then all the antiderivatives f on I have the form of f plus c. In other words, you can add any constant to your antiderivative, and it is an antiderivative still. And so visually, let me take you to Desmos. That's not Desmos. Here we go. So I have a function here. Now this is an antiderivative of something, but here's the part that gets interesting here. I can add a constant. All these constants I can add. And if I add that, it's still an antiderivative of an original function because we have a whole family where, because the derivative of all these would be 0. So if you took the derivative of all 6 of these functions, or 7 of them, they all have the same derivative. That means they're all antiderivatives. So what does it look like? Well, if I choose this one, it's just shifted up 1. Shifted up, this one will be shifted up 2. The next one's shifted up 3. This one's down 1, down 2, down 3. Let me screenshot that and point something out here. So these derivatives are all the same. Let me do a finer writing. And how do we know? If we take any x value and find the slope of the tangent line, all of them will have the same slope. In other words, they all have the same derivative. If I take another point and find the slope at that x value, they all have the same slope. That means the derivative for all these functions are the same for every value of x. And so that's kind of the concept that's going on here. The derivatives of all those are the same. Let me delete this. And so you end up with a family of antiderivatives, and they all work. And so that's why we always put a plus c when we take an antiderivative. Okay? So here's some examples, and go ahead and pause this video and see if you can figure these out. Okay, let's go back to this one. So the antiderivative, we'll call big F, would be x to the 4th plus c. How do we know for right? What's the derivative of that? You bring the 4 in front and decrease that by 1, and bam, you get that. And the derivative constant 0. Okay, how'd you do on the next one? We will see this would be arctan of x. Why? Because we know the derivative of arctan of x is 1 over 1 plus x squared. And I can add a c here. That would give me all the antiderivatives. If I didn't have a c, it would give me one antiderivative. And then the last one, we ask ourselves, the derivative of what is sine? And a lot of you might say cosine, and you would be wrong. Because check, what's the derivative of cosine? Minus sine, but that's positive sine. So I actually need a negative here, and it works. What's the derivative of that? Well, derivative of cosine is minus sine. Minus and a minus become positive sine. So basically, you're thinking backwards. What the derivative of what equals my original function? So that leads to the question, how do we indicate we want an antiderivative? So we knew in chapter 3, if you have a d dx in front, that means find the derivative. Or an f prime, we did that. That means take the derivative. How do you tell someone to take the antiderivative without writing find the antiderivative? So we have a new symbol, and it's this squiggly s. Think of it as s, and you'll see why it's like an s. So you have the squiggly s-looking thing, elongated s. That means find the antiderivative of f of x. And what's that dx? Well, we're going to explain further. But so now you should just know the squiggly says find the antiderivative. The f of x is the integrand, or what you're trying to find the antiderivative of. And for now, this dx tells you what your variable is. X is our variable. It will have more meaning in the next lesson, but that's what we'll stick with now. So example 2, using our new notation, this says, find the antiderivative of this if our variable is x. And so we ask ourselves, the derivative of what is x squared? I mean, x squared. Because if you take the derivative of that, you get that. And you ask yourself, the derivative of what is 4? And say, I know, it's going to be 4x. Because the derivative of 4x is 4. So the antiderivative of 4 is 4x. And that is a antiderivative. If you want all of them, you say plus any constant c. All right, try b. You can pause and then see the answer. So the answer to b would be tan x plus c. Why? The derivative of tan, we all know, is secant squared. Bam, we're done. All right, so we had a power rule for derivatives. Now we have power rule for integration. That word indefinite, if that throws you off, that just means you don't have bounds, which doesn't make sense to you now until we get to chapter or section 2. But indefinite means there's no numbers here. Don't worry too much, that'll make more sense in the coming sections. But we're doing the backwards derivative. So in the derivative, we decrease that by 1, right? So if we're going the backwards, we're going to increase that by 1. That's why you do p plus 1. In the derivative, you put the p in front. In the antiderivative, instead of multiplying by p, you divide by your exponent. So at p plus 1, you're going to divide by that. So this is the general formula for x to a power for finding the antiderivative. A little note, and we'll see why, your exponent can't be -1. And it'll make sense because then you're dividing by 0. We'll just think about it. If you had a -1 plus 1, you're dividing by 0, and all of a sudden that's very confusing. Couple more rules. If you have a function times a constant, and you want the antiderivative, you can take that constant out and find the antiderivative of just your function, then multiply by that constant later. And then, if you have the integral of 2 separate functions and you're adding them, it's the same as the integral of them added together. So you can combine or separate. So if you start with 2 functions together, you can separate it to 2 separate functions. How does that help us? We're going to apply all the rules we learned to all the example 3s. You can pause and try these and see how you do. So for A, I'm going to rewrite this like this. And I'm applying the sum rule. I can take a bunch of things that are added or subtracted and separate it to each individual integral. Okay? Now the next rule, I'm going to apply the constant. If I have a constant inside, I can pull it out in front. So what I'm going to do is bring the 3 out in front. And take the 5 out in front. And I'm going to write that to half power. And all these have dx's. Okay, now I just use the power rule to find the final answer. So it's 3. I add 1 to the exponent and I divide by that. 2. The antiderivative of 1 is x. And x to the 1/2, I add 1 to the exponent, so it's 3/2, and I divide by that. And if I simplify this, I get x to the 6/2 plus 2x. And then I multiply by the reciprocal. So it's going to be times 2/3. So it's going to be minus 10x to the 3/2 over 3 plus c. So that's how you do the antiderivative of A using all the rules. Now, eventually, you're not going to separate it out like this, but this is why it works. We have to use only the rules we know to simplify this. All right, try B. I'm going to erase all this. You can pause. try it out, and then I will do B for you. So B, we got to rewrite this thing. I am going to divide each one by x squared first. So I'm going to get 4x to the 17th minus 5x to the negative 10th. Then I'm going to use my rule of separating into two separate integrals. Then I'm going to use my rule where I can factor out a constant. These each should have a dx here, by the way. Then I'm going to use my power rule where I add 1 to the exponent and divide by that. And I add 1 to the exponent and I divide by that. And I have a plus c. And to simplify that further, this will be 2x to the 18th over 9. I just divided both these by 2. And then I have these two negatives are going to make a plus. So it's plus 5 over 9. And the negative moves that to the bottom. And plus c. So that's my antiderivative for B. Let's do C. So to do C, we don't have a product rule for antiderivatives. So we're just going to multiply that out. We're going to get 2x squared, and then we're going to get 2x minus 5x minus 3x minus 5. Let me double check that. That's going to be 2x minus 5 is negative 3. That's correct. Then we use our rule where we separate this into three separate integrals. Then we pull constants out. Then we find antiderivatives. We add 1 to the exponent, then divide by that. We add 1 to the exponent and divide by that. Technically, on this next one, we're adding 1 to the exponent. Technically, it's 1x to the 0. So we're going to add 1 to the exponent, so it's going to be 1 over 1 plus a constant. So there's our answer for C. All right, using all these properties that we learned. More examples. So I'm just going to do these because these are common integrals you need to know, or antiderivatives. You ask yourself, the derivative of what is 1 over x? And you should say ln x. And technically it's ln absolute x. Not going to go into the details of why, but it is. And just a side note, whoa. Same thing for that. That's going to be ln absolute x. It's going to be the same either way. And, okay, I should have told you, go ahead and pause and try these. I'm going to finish off these, so go ahead and give yourself a chance to try these on your own. The more you do, the better off you are, okay? All right, the next one, you have to look at that and say, hey, the derivative of what equals that? You might be a little bit confused, but you just have to think about it, okay? Think. Here is your answer. And actually, let me back up on that previous one. I don't think we ever have this case. I was actually thinking of derivatives, so let's stick with that. So the integral of 1 over x is ln absolute x. All right, B, what is the answer to that? The derivative of what is that? And if you remember, it's arc sine x. I forgot my plus c on that one, by the way. Yeah, derivative of arc sine is that. And that's just memorizing. The derivative of what is e to the x? I am my own grandpa, so that's e to the x plus c. Double check, take the derivative of that, and make sure you get that. And then the last one, the derivative of what is secant tangent, and you should remember secant x. The derivative of secant is secant tangent. That is one of the derivatives that you are supposed to know. All right, we have a couple more examples and we will be done. 2 examples. So solve the initial value problem. And what does that mean, initial value problem? And what does it mean, solve? So solve, I have f prime. When it says solve, we want f. So in other words, we want the antiderivative, the original function. So f of x, and we use our power rule. I add 1 to the exponent and divide by that. Same thing, I add 1 to the exponent and divide by that, and I have a plus c. So here's our problem. We have this function, but we don't know c. But if you have what's called an initial value problem, they give you an initial value, and from that, you can solve for c. So you can find a particular solution. So this is called a general solution because c could be anything, and you have multiple solutions. So that's a general. If you want a specific solution, you can solve for c. So they tell us, I'll do it in blue, f of 1 equals 1/3. What does that say? If I plug 1 in for x, this will equal 1/3. So that's what I'm going to do. F of 1 equals 1 cubed over 3 minus 1 squared plus c equals 1/3. Well, I get 1/3 minus 1 plus c equals 1/3. Well, first thing I notice, I can subtract 1/3 from both sides. Then I can add 1 to both sides. And now I have found c. So now that I know what c is, I'm going to take that and plug it in. So now I have, this is called the particular solution. Oops, it's minus x squared. So this, I will tell you, is called the general solution. This is called the particular solution. So that terminology be used. This is a specific, and that's the only one that meets the initial conditions, the initial value. That's why it's called initial value problem. If you were told specifically at a point what the y value is, now you know the exact solution. Now tie that in to Desmos. If they told us, okay, these are a bunch of possible solutions. Could be any of these. You don't know which one it is because they all work. But if they told you at time t equals 0, your function equals 3, or when x is 0, your function equals 3, you say, here's 0. Oh, right there. It's the purple one. The purple is the solution because that's the only one fits condition of 0, 3. So if you're told a specific point, you can actually figure out which one of these graphs is the actual solution. So these are all general solutions. When you give a specific point, you have found a particular one, the solution. So if you're given the point, I don't know, 1, 2, here's 1, here's 2, right there. There's 1, 2. So the solution would be this red one here. So you can find the exact solution if you're given initial conditions. So that's what the initial value problem is. And this will be a common thing, and it needs to be something you're able to do. So this is another initial value problem, but just in the context of position, velocity, and acceleration. So from the last chapter, just to remember, if you have a position function, could be x, could be y, could be s, that's your position. Then you knew this thing called velocity. And how do you find velocity? You learned you take the derivative of position. Very important. These are very common questions on the AP test. Then you learn the term acceleration. And then that was called a of t. But then you learned that's the derivative of velocity. You should have. Or it's the second derivative of position. So these are all things that we learned in chapter 3 and 4. Now in chapter 5, we can go backwards. If you have the acceleration and you want velocity, you find the antiderivative and go backwards. If you have the velocity and you want the position, you do the antiderivative and you go backwards. So we're able now to start with acceleration and find velocity and position, where in chapter 3 and 4 we started with position and we took the derivative and moved down this chain. So this is very important. Every year there's always an FRQ. Out of the 6, there's one dedicated to position, velocity, and acceleration. So you want to make sure you understand this. So to summarize, to move down, you take the derivative. To move up, you take the antiderivative. That's an antiderivative sign, by the way, not an S. So we're going to use this concept to do number 6. So if you drop an object, it always falls at a constant acceleration of negative 9.8 meters per second squared. Any falling object on the earth has that acceleration. Now they tell you a story. Suppose a stone is thrown upwards at t equals 0 with this velocity from a cliff that's 100 feet above a river. So we need to assume where 0 is. We're going to assume the river is 0. So the height is going to start at 100. And the velocity is going to already be going 40 meters per second. Okay? So part A says find the velocity. Well, what do we know so far? We know acceleration function is this. So how do we find velocity? Well, we go backwards, right? To go from acceleration to velocity, we take the antiderivative of the acceleration. So we would say the velocity is the antiderivative of that. And so we ask ourselves, the derivative of what is 9.8? And we would say 9.8t. Double check. Is the derivative of that equal that? Yes. But don't forget your plus c. So there are an infinite number of velocity functions. How do we know which one is for this particular case? Well, we have an initial value problem. When t is 0, we have a velocity of 40. In other words, we're told v of 0 is 40. Now, I'm kind of ignoring units here. I probably shouldn't, but I just want to get you through the basic concepts and not to freak out about the units. So we're going to use those initial values. So in other words, if I plug in 0 for t, my velocity should be 40. Well, 9 times 0 is 0, so c is 40. So now I have found c. I'll call this C1 because it's particular to this equation we just have done. So now you know c, you plug it in here and you have the actual velocity function. Instead of having a general solution, you have a specific. All right, so there is our velocity of our object. Awesome. We can plug in any time here and find our velocity. So if you're throwing the object up, that's what it is. All right, part B, find the position of the object. Well, they're calling it y of t. So the question is, how do I go from velocity to position? I integrate. Remember, if you're going this way, you take derivative. You're going up, you integrate. So I probably should write integrate. Integration. So if I have my velocity, how do I get acceleration? I integrate the velocity. Well, how do I do the antiderivative? I add 1 to the exponent of t and I divide by that. And then the antiderivative of 40 is 40t because the derivative of 40t is 40. And then I have a plus c. Uh-oh, how do I find c? Because I need, whoops, why did I put a? Hopefully you caught that. It's position y. I'm going backwards, not forwards. So to go from velocity to position, I integrate. So I integrate my velocity. And then I can simplify this. My position function will be negative, what's that, 4.9? 4.9 t squared. I just divided 9.8 by 2. Plus 40t plus c. Can I find c? Huh. I can. Check this out. You're told at t equals 40, you're 100 feet above the river. In other words, the height at time 0 is 100. That's your initial value that you're given. So if y at 0 is 100, I'm going to plug 0 in for all my t's. And that better equal 100. The good news, that's 0, c is 100. I have found my c, and now since I found that constant, I will plug it in for that c there. You see? And I probably should have called this c2 to distinguish it from c1 over here. So now I have my position function. I'll call it y of t, since that's what I called it at the beginning. Negative 4.9 t squared plus 40t plus 100. So now I have found my position function. What is the maximum height? Okay, this is an optimization problem. I want to maximize my height. Well, y of t is my height. Where do maximums and minimums occur? They occur at critical points and endpoints. So I need to find my critical points, meaning I need the derivative of y, which is interesting in itself. That's going to be negative 9.8t plus 40. I set that equal to 0. Subtract 40 from both sides. Divide both sides by negative 9.8. And I have my time. 40 over 9.8. Now, I can throw that in the calculator and get an approximate answer here. 40 divided by 9.8. And I get, ooh, I don't want to do that. I'll just leave it like that. I could do this. Multiply top and bottom by 10. Divide top and bottom by 2. 45, 49. So 200 over 49 seconds. Is it feet per second? Yeah. So that's the amount of time to get to the highest point. So what is the maximum height? I got to plug that number into my height equation. Okay? So I'm going to cheat and take a look and see what my answer is here. I am going to get, let's plug it in here. It's part C. It's going to be 182, about 182 meters. So now how did I do that? I took the time where it's the highest and I plug it in to the position function because that tells me the position, so that's the height. Now, what's interesting, I don't know if you caught this, but the derivative of y is velocity. So think about this logically. You found when the velocity is 0. Well, that makes sense. If you throw an object in the air, it's going to stop and then it's going to start falling down. When the velocity is 0, that's when it's at the highest point. And so a couple of things to point out here. There's only one critical point. So that critical point has to be an extreme, excuse me, take that back. There's only one relative extrema. So that has to be the absolute extrema. So we know this is either the absolute time of the maximum or minimum, but logically, if you're throwing something in the air and then it starts dropping, that's going to be the maximum. So that's how we get the maximum height above the river. Now the next question, what speed does an object strike the river? I don't know, but here's our cliff, and we throw something in the air, and it hits the river. What do we know when it hits the river? Do we know the time? Do we know the velocity? Do we know the acceleration? We actually do know the acceleration because it's always negative 9.8 meters per second squared. Or do we know the height? We do know the height. When it hits the ground, the height is 0. That's what we're going to use to find when it hits the ground. So y of t is this function. And you want to know when this is 0 because that will give us the time when it hits the ground. Now, to solve this, we're going to have to use a quadratic formula. If you use the quadratic formula, you're going to get 2 times, but one of your time is going to be negative. It's about negative 2. Your other time is going to be positive. It's going to be about 10.2. These are rounded off using the quadratic formula. Obviously, you don't have negative time. You can't go backwards in time. So the time when it strikes the ground or the river is 10.2 seconds later. So they're asking for the velocity. I need to find the velocity at 10.2. So I plug that into my velocity function up there. So it's negative 9.8 times 10.2 plus 40. And so that's going to give me a final velocity of actually negative 60. But speed is the absolute value of that because speed doesn't care about direction. So the speed will be 60 meters per second. So that is an example of an application of using antiderivatives in terms of velocity, position, acceleration with initial values. And that is the end of this lesson.